Good afternoon to all the participants and Dr. Sunil, today's speaker. So, although the attendance is little poor, it seems, but by the time I think Dr. Sunil start, I think the attendance would be good. And in this session 3 on 24th of June, Dr. Sunil Yadav, whom I introduced yesterday afternoon also, who is from basically Indian Institute of Information Technology, Allahabad, Prayagraj. And he would be delivering a talk on reconfigurable intelligent services enabled wireless communication. So that is a very interesting research area which has opened in last couple of years. So those who are interested in this area, they should get out of this. So over to Dr. Sunil. So you can share and you may start.
Yeah,
Dr.
thank you,
Sunil.
sir. So, okay. So let me share the slides. I think it's visible. Slides are visible.
Yes, slides are visible, quite visible.
Okay, sir. Okay.
So you start a little slow. The participants are still joining.
Sure, sir. Sure.
Because few of them might have a little late lunch also, it seems. Anyway.
Fine, sir. Fine. Okay. So good afternoon, everyone. So today's talk is basically regarding the reconfigurable intelligent surfaces enabled wireless communication. As sir has already told that this is the very recent area where the people are looking for designing and the performance of wireless communication with the help of the some it's basically a totally different technology that is basically known as the reconfigurable intelligent surfaces. We know these surfaces. There are the number of surfaces we already know as far as the physics and the optics are concerned. But this is the first time that the people are actually introducing the such type of surfaces. We'll talk about what type of surfaces we are talking about. Although, so different surfaces the people are talking about in terms of the wireless communication, basically. Because the people initially we are looking for this some software defined radios, and because everyone knows in a wireless communication what is a meaning of software defined radios, because they are being controlled by by means of some software. Okay, so similar to that, there is another technology basically which is available or which is going to be implemented very soon, that is known as reconfigurable intelligent surfaces, so that we can reconfigure our surfaces intelligently for transmitting a signal from one end to the another end. So this is very interesting phenomena basically. It is as similar as, not as similar as, but it is as analogous as we are talking about the cognitive radio, because the cognitive radios are also very intelligent radios which can reconfigure its own parameter according to the different environmental condition. But here the idea is slightly different, okay, which needs to be considered definitely in case of the wireless communication, which is a very prominent area of research. Okay, so I'll start with the some introduction related to the what is the current trend and the what is the future trends in the wireless communication, and which basically lay the foundation for the need of reconfigurable intelligent surfaces. Then we'll discuss about the RIS, that is reconfigurable intelligent surfaces. Then we'll form the basic mathematical background for RIS, because it is very necessary to model the wireless communication systems and networks mathematically, so that we can analyze the performances before implementing and the deployment before deploying these networks which are enabled with the RIS technology. So it's a very important to investigate the mathematical background for such surfaces. Then because we are integrating the RIS in the wireless communication, so again it is very important to have the channel models for the RIS enabled wireless communications. And then we will discuss about the performance analysis related to the particular use case, and then it will be validated by the simulation studies, and as we have done yesterday's in a yesterday class, basically how to simplify the systems and how to verify the performance of how to verify the results basically with the help of the Monte Carlo simulations and the Mathematica software basically. So I'll start with the basics of futures. What is the future of wireless communication basically? So let me first discuss about the basics of or the basic need for the future wireless communications. So there is a report which was shared by the Cisco in 2019, and it was proposed that it is expected to have around 28.5 billions of network devices and connections throughout the world basically, and out of which 12.3 billions are only mobile ready device and connections. So because this definitely if you see the numbers, 28.5 billions and the 12.3 billions of mobile devices, so this basically has set up a huge demand over the mobile data traffic, and which is basically expected to grow with around 77 exabytes. That is 77 into 10 raised to the power of 18 bytes basically. At the same time, because the people are talking about the 5G services, and in some of the countries the 5G services is already been started, and hopefully in India also next 2-3 years we'll have some sort of 5G devices as well as the 5G services also. So if you see the deployment of the 5G services, they have led the basically a new vision to the mobile communication. And once we are talking about the 5G era, so and 5G services and 5G applications, so these applications basically impose a huge demand and requirement on the cellular networks. And what are these demands and requirements basically? We have to we have to improve the energy efficiency of the networks or the cellular networks. We have to improve the spectrum efficiency, which is a very basic requirement to have the better spectrum efficiency. At the same time, we have to improve the reliability of the networks and the security. Definitely, the security is the major concern, as we have already discussed yesterday. Also, there is a physical layer security, cryptography approaches, and so on. So it is very prime concern, basically the security. But here, the prime concern is a flexible design also, because we want to we want to manipulate the design of the cellular systems according to our need, because we don't want to start the new infrastructure from the scratch. With this having the same infrastructure, if we can design our component and the devices and the algorithms in such a way so that it will be flexible to manipulate any time, so that will be a good for the cellular networks basically, and for the future communications as well, because it is very difficult to change the overall infrastructure every time. So I can give you one example. As we currently, what is happening, we generally in our cellular networks, we deal with the orthogonal multiple access techniques, and recently there is another technology which is emerged, which is known as a non-orthogonal multiple access, that is NOMA. But what happens if you are going to implement the NOMA, you have to change the infrastructure from scratch. So then it is very difficult to deploy these, the new technology like NOMA in a current infrastructure. It is very difficult. So, however, for a new applications, for example, if you are talking about the IoT systems and which are or new services which you want to deploy, which are not available yet, you can apply these NOMA techniques. Okay, but currently you have to deal with your okay. So that's why the flexible designs are very much required. That's why the software defined radios comes into the picture, and they have served a purpose very well up to some extent. Okay, but these are the few requirements of your future wireless communication, which we needs to understand and which we needs to analyze further. Okay, so to deal with these requirements, there are the three major use cases basically, which are very popular, and the researchers are basically interested to implement these use cases in the future generation networks like 5G and beyond 5G networks or 6G or so. So the first use case is basically the ultra reliable low latency communication. The next is the enhanced mobile broadband, and the third is the massive machine type communication. So these are the these use cases are very important, and they can fulfill these certain requirements which are needed for the future wireless communication. But we need to have some sort of physical layer technologies which can support these use cases, and we are very fortunate that we are fortunate that we have number of physical layer approaches or technology which can support these use cases. So the few of them are like cognitive radio systems, the cooperative relaying communication, and the which is one is the very popular, that is a massive MIMO, a massive multiple input multiple output millimeter wave, which I just named the NOMA, that is non-orthogonal multiple access. Device to device communication is also one of them. Vehicular to vehicular communication, as we talked about yesterday's lecture, this is also a technology where we can support these requirements, and we can support these use cases which are having the diverse requirements for the future wireless communication. So and there's a number of other technologies as well at the physical layer which can available for or which are available to serve these requirements basically. But however, there are some challenges. There are many challenges in wireless communication, and the few challenges I have named here. Let's say there is number one is resource and spectrum utilizations. So this is one of the major challenge basically for wireless communication. And in the recent era, we have seen that the cognitive radio technology is one of the one of the technology which can overcome this challenge by by smartly adjusting its own parameter in order to serve in order to exploit the efficient spectrum resources basically, or which can utilize the spectrum in a more better way. So that we have seen. Similarly, there is another challenge, that is a communication infrastructure. One more challenge is wireless access techniques. Another is coding and modulation, and one is very very major challenge, that is a interference management, which we are always investigating the performance of any system. So we always deal with the interference kind of thing. So we need to manage the interferences at the same time. So there are various challenges available for the wireless communication, and we need to deal and we need to tackle with these challenges. But here the major challenge which we want to have is basically the controllable and programmable radio environment, which is a major challenge, because what is happening if we want to design, for example, just have an example, if we want to design a wireless network which can provide an uninterrupted connectivity and quality of service for the number of users and the devices in a harsh propagation environment. So you cannot able to design such networks basically, because of you don't have your control over the wireless propagation medium. Okay, so the one of the major challenges basically to have the controllable and the programmable radio environment. Okay, why you are not able to design a wireless network which is very which can basically provide an uninterrupted connectivity and quality of service, because of some reasons. So let me introduce a few of the reasons here. The first reason is a deep feeding. The basic fundamental of the deep feeding, because it is because of the interaction of some transmitted wave with the surrounding objects, and then there are the discrete and its destructive interference at the receiver, because at the receiver side all the signal will be added in the destructive manner, and your basically signal go into the deep field. So this is one of the reasons of having the uncontrollable and the random behavior of the radio environment. So which is due to which we are not able to get the controllable and the programmable radio environment. The another major reason is basically the severe attenuation, which is a very basic that we know the path loss phenomena, shadowing, and the non-light line of sight transmissions basically. So due to this, we have the severe attenuations also. The one more reason is basically the inter-symbol interference, which is everyone knows, because this is due to the different copies of, or the runtimes of the multipath component basically. So this is one of the crucial and the critical parameter for the uncontrollable and the random behavior of the propagation medium. And this definitely we have already talked about in a yesterday class, that is a Doppler effect. Because once we are talking about the vehicular scenarios and vehicular communication, so definitely we need to deal with the Doppler effect, because the objects or the vehicles will be of very high speed, and we need to tackle this impact basically, this impact of Doppler. So these are few reasons, because of which we are not able to achieve the controllable and the programmable radio environment. Because what we want to control and program the environment according to our need. Whenever we require, we can have this type of we can have this direction of the signal. Whenever we require the signal in this particular direction, so we can program it, and accordingly my signal will be transmitted from one end to the desired direction basically, to the receiver. So this we want, but unfortunately we are not able to get the, even after we are last 30 to 40 years of wireless communication era, we are not able to achieve this perfectly. Okay, and definitely this is a huge challenge further also, to have the controllable and programmable era. So the idea is basically, so if we want to get the controllable and the programmable radio environment, we have to deal with these factors. Means we have to deal with the deep feeding scenario, we have to deal with the severe attenuation problem, we have to tackle the inter-symbol interference phenomena, and we have also need to look into the Doppler impacts, basically Doppler effect. So these we need to understand what is happening basically, and how to overcome these issues. So let me introduce a very basic need why we require the controllable and the programmable radio environment. So let us assume this as a simple example. There is a transmitter and there is a receiver, and there is an obstacle in between. Let us assume there is this obstacle. Let us assume it is a wall. There is a room, and the receiver is inside the room, and there is a transmitter, and a transmitter is transmitting some data, and the receiver has to receive that data. But due to the obstacle, which is considered, just for example, assume a wall in between. So due to the wall penetration of the when the signal is penetrating through the wall, so what you will receive a signal with a lesser strength basically, with a few the strength is of few order basically. Or you may say the loss is basically, typically if I'll use a typical value, it is around like minus 25 dB to 30 dB basically. So you will get the that much amount of loss in your received signal at the receiver side. But at the same time, so this is because of the you have the line of sight, direct line of sight component available, although, but there is an obstacle present in between. So your strength or the received signal power is being reduced at the receiver side, and it is being reduced, let us assume, for minus 25 dB for example. But at the same time, you have an extra path in the room. So you are still in the room, and the transmitter is transmitting a signal. There is a line of sight available, which is unfortunately obstructed by some obstacle or a wall. So, but let's say there is a window in a room. So your signal has an extra path. It can pass through a window, strike to some wall, and then reverse to and then back to your receiver side. So we are assuming this particular case here, that is, there is a extra path which is available. So you can assume like here is some sort of, for example, we can say like this. There is some window. There is some window here. There is some window here. So your signal is basically passing through this window, and in a room there is a wall. So the signal will strike to the wall and then back to the or then receive to the receiver side. So this is, you can say, the line of sight component basically. So, but what is happening with this wall? Because I'm interested in this wall basically. Even after having this extra path striking to this wall, your signal is going to be received at the receiver side definitely, and you will get at least a good amount of signal is sent at the receiver, so that your your signal can be received and your work can be completed. But I'm interested in this surface, basically this wall, where the signal is being striked basically. So let me give some phenomena related to this wall. So this is a basic structure which I have prepared here. So let us assume the wall is having a smooth edges in case. So if you can see this phenomena, if the wall is having a smooth edges, so whatever signal is incident here, it is being reflected in a particular direction. Okay, it can be reflected in a particular direction. So this phenomena generally known as the reflection phenomena. Okay. Similarly, if the surface of the wall is rough surface or having the rough edges, so whenever the signal is struck to the rough edges, it will be scattered in a different directions, as you can see from this figure, and then scattering phenomena will come into the picture. Okay. At the same time, if there is a edges, if it is if the wall has these sharp edges, okay, like the corners of a building, okay, or the corners, let's say there is some you can say some painting or so is hanging on the wall, so the signal may strike to the sharp edges of this painting, okay, and then it can be further deflected in a different directions. So the diffraction phenomena comes into the picture. So, and you know the basics of these, basically there is the reflection, scattering phenomena, diffractions. These are are basically deal in the physics and the optical physics basically, and these are the widely used phenomena in physics. So if we talk about the wireless communication itself, we are generally deal with this particular phenomena, that is a scattering phenomena, as we have seen yesterday also in a previous in the V2V lecture. Basically, that is we have to deal with the single and the multiple scattering phenomena to deal. So here the basic idea is to differentiate, or basically to categorize the wall, the surface, basically, rather than the wall, I should say the surface. So the surface should be categorized in a different manner, so that you can predict whether it is a smooth surface, it is a rough surface, or it is a sharp surface, so that according to that we can have the different phenomena, and under these phenomena we can model, we can design, we can characterize this characterize our system basically. Okay, so if you go through the current wireless literature, you generally encountered with this scattering phenomena most of the time. Okay, but here we have seen one interesting fact also. If the surface is smooth, however, if you see the wireless communication in the current era of the wireless communication, generally what happens once the signal is being transmitted, it is being struck through various buildings, various trees, various terrains and so, and the signal is being scattered in a different directions. Okay, and you don't have the control over the these signals which are being scattered in a different directions. So our aim is to, if we can control a direction, okay, if we can control the direction of the signal, the scattered signal basically, so we can simply say that our propagation environment can be controlled and programmed accordingly. Okay, so this is the basic aim here, to control the direction of the signal. So once, if we are able to control the direction of the signal, we can transmit the data in a particular direction where the receiver is basically placed or the position. Okay, so but this phenomena, which is a reflection phenomena, so we got to have some sort of information that let us design a surface, which can reflected all the incident signals, okay, or the incident beams basically, and according to that, and but at the same time the surface should be designed in such a manner so that it can be controlled also, because we need to control the direction of the outgoing signal. Let the signal coming to the surface, and it should be controlled in the different direction. So if you see the scattering phenomenon, it is very difficult, but there is a some we can say there is some hope, so that we can design a surface with the help of this reflection phenomena. So let us discuss about this reflection phenomena with the surfaces, different surfaces basically. So let us consider a very simple basic example, a metal surface. If you see the metal surface, if some signal is incidented on the metal surface, it can go into the different direction in a particular direction. Okay, and this particular direction which I have mentioned here with the help of this theta r, that is the angle of reflection, and theta I is the angle of incident basically. This is happening because when I'm saying it is incidented, or you can say the signal is coming into a surface and it is bounced back in a particular direction. This is because of the constant surface impedance, because the metal surface, we are assuming the surface impedance at each point is coherence, basically the constant throughout the surface. It is same. Okay, the impedance is same. Okay, and this can be it is a very popular law, that is Snell's law. So that is the theta is equal to the theta r can be achieved if we have the the constant surface impedance on the metal surface. Okay, but here what is happening with this particular law, because the surface impedance is constant throughout, so what we are actually getting is still we are not able to control our outgoing signal basically, which is being reflected from the surface, because the surface impedance is constant at each and every point of the surface. So but this fact basically basically lays the foundation for the controllable systems basically, or a controllable surfaces. So let us discuss the another surface, that is the ideal meta surface. So when I'm saying the ideal means this is the one surface here. Let me first introduce what is the meta surface here. So meta surface is nothing but the two-dimensional meta materials. Okay, generally we know we know these meta material as a planar arrays of these meta surfaces as the planar arrays of the meta materials. Okay, and the meta material is a typical material basically, which is having a negative refractive index as a property. Okay, and it is a widely used. You can use it. You can find several applications of the meta materials. If you are interested, you can go to the some of the research papers of the meta materials, and you can find the interesting properties of the meta surfaces and the meta materials. So the meta material applications are basically not limited to these which I am mentioning here, like optical filters. They are very popular in design. Some medical devices also having the meta materials to design. Some high frequency battlefield communication devices are also being developed by the help of meta materials. So they have the unique properties basically. So the one of the properties also here, that the meta surfaces, which are basically the two-dimensional meta materials, with the help of this meta material, whatever signal is incidented can be controlled. Okay, or the direction of the outgoing signal, basically the phase of the outgoing or the reflected signal, can be controlled by adjusting the surface impedance of the meta surface. So this can be controlled here. So which I mentioned here, the altering the surface impedance to phase shift reflection. So whatever, if this is the reflected wave, so if we can adjust, or if we can alter the surface impedance of this surface basically, of this meta material, so we can control our beam, that is a reflected beam. And once the beam is controlled, so we can have the we can get the you can say the desired direction basically. You can have the desired direction of the propagation wave. So this is the idea. But this is the ideal meta surface, and it is very difficult to get the ideal surface or ideal systems. Okay, so let's have the practical meta surface. Let us assume. So what is happening here in the practical meta surface, basically we have what we have done, we have discretized the elements. So there are the 24 elements in this particular sheet. So these 24 elements are basically, or you can say that each element has its own reflecting properties, and there are the 24 elements available here. So we have discretized these elements in a surface, and basically the size of the surface is size of the each element is of the sub lambda size. So here the sub lambda size is basically you can say like this, that this particular element has a lambda by 5, the typical size lambda by 5, the sub lambda by size, basically lambda by 5 of lambda by 5 size of element. And what is the best thing, that each element has its constant phase shift. So what is happening? So you can control the phase of each element according to your need. So let us assume if this is striked here, if this signal is incidented on this particular element, so you can control this direction. You can control this particular direction. If it is struck at this element, so if you want to have this in a and let's say assume your mobile device is somewhere here, so you can control in this particular direction. If it is struck at this element, so you can control in this particular direction. So this is the beauty of this meta surface, that each element can be controlled. Each element can be controlled. And how it will be controlled? It will be controlled by adjusting the surface impedance of the surface, basically the meta surface. Okay, so we can conclude here like with a statement that by adjusting the phase shifts of reflecting element, by adjusting the phase shifts. What I'm talking about the phase shift, these basically the theta r, this which is a reflecting angle theta r. So if we can adjust, or let me finish this statement here. So by adjusting the phase shift of the reflecting elements, the reflected signals can be reconfigured to propagate towards the desired direction of the receiver. Okay, and how to achieve this particular adjustment in the phase shift? With the help of this, altering the phase surface impedance to the phase shift reflection. That is basically this idea, altering the surface impedance. So if we can adjust our surface impedance, we can adjust the phase shift, and if we are able to control our phase shift or the phase of the reflecting wave, then our aim is almost completed, because we have the desired direction to receive the signal in the at the respective users or the device. Okay, so this is the basic aim here. And how it will be basically achieved? This can be achieved with the help of the generalized Snell's law. So the generalized Snell's law, simply you can say here, the sine theta I minus of sine theta r, that is a typical Snell's law formula, but here they have modified it in the generalized way. This is the phi r y, that is a surface impedance. So this d by dy, that is a we are calculating the differentiation of this quantity. That is, we are adjusting the surface impedance. Okay, so by having this formula, we can get the we can adjust the surface impedance, and if we are able to adjust the surface impedance, it is automatically we are adjusting the phase shift. And if we are adjusting the phase shift, which indicates that we can reconfigure our signal to propagate in a desired direction where the receiver is basically placed. Okay, so this is the basic idea. Okay, let me give you some further detail related to this RIS also. So yeah, so this is basically basically the starting of the reconfigurable intelligent surfaces with the help of the meta surfaces. So why we generally known as the reconfigurable intelligent surface? The reconfigurable mean the property can be changed. Means you can alter the surface impedance. You can accordingly manage the phase shift basically. And why it is intelligent? It is intelligent in a sense that is it can be programmed in a real time, and it can be controlled anytime, because it has the controllable surface. And because the surface here, it's a two-dimensional planar array of metamaterials, which is basically has the capability of adjusting its parameters of the surface impedance, which is not possible in a metal surface, because there in a metal surface you have the constant amplitude, constant impedance everywhere. Okay, So that's why this is basically known as the reconfigurable intelligent surface. Okay, so although the surfaces are very, it's already been proposed few, numbers of years back, the people are using the metamaterial surfaces, but in the only, in the last 2-3 years they've been introduced this in the wireless communication, because there are the challenges while you are introducing these in a wireless communication. So uh, let me give you the further detail, some statements here. The reconfigurable intelligent surfaces are typically constructed by the planar artificial meta surfaces, which are having the number of passive reflecting elements. So when I'm saying the passive reflecting elements, my meaning is basically the elements do not have any processing unit which can process the RF signals basically. Okay, okay. We'll discuss about what is the meaning of the passive reflecting elements. But at which the second point, which I have already discussed, that the RIS can be controlled by smartly adjusting the amplitude and the phase of the incoming electromagnetic waves, and then you can adjust the direction and the strength of the wave, highly controllable at the receiver side. So this basically can be easily observed with this particular figure here. So there is a transmitter. If the transmitter is transmitting some information to the reconfigurable intelligent surface, which is controlled with the help of a controller unit, and you can, by adjusting the surface impedance of this particular surface, you can get the by adjusting the surface of this particular RIS element, you can control the phase, and accordingly you have the controllable beam in a desired direction of the receiver basically. So if the receiver is placed somewhere here, let's say if the receiver is placed here, in this particular case, let us assume the mobile device is placed here, so you can have the beam to be controlled in this direction. If the receiver is somewhere placed here, so you can adjust the parameter or the surface impedance in such a way so that the beam should be in this particular direction. So this is the beauty of this reconfigurable surfaces basically. So you can reconfigure, and you can program it anytime in a real time itself, and because of it is a metamaterial, so they are very cheaper and very easily available. Okay, the metamaterials are very cheaper and very easily available compared to the other technologies. Okay, now the what basically the RIS required basically here. So if you see the RIS is only consist of a surface and the controller unit. That's it. Okay, but how to design this? So let me give you a brief idea about the reconfigurable surfaces basically. The reconfigurable surfaces may be of single layer, and there may be a multiple layers basically. Okay, it depends on the designers how they actually wants to design the surfaces. They may design a single layer of a surface, and they may have the multiple layers of the surfaces. It's all about the VLSI designers to design, or some material designers to design the surfaces basically. Those people are actually working in this particular area of designing the surfaces. So we are not going into the detail of that, how to design and something like this, but we can have an idea that if, let us assume, if you want to design, if you want to have the RIS with three layers. So what is the meaning of three layers? So basically the three layers is basically divided into three different layers. First layer is known as the outer layer, the second layer is known as the middle layer, and the third layer is known as the last layer or the back layer basically. Okay, so if we'll talk about the first layer, so the first layer generally has the large number of reflecting elements, like if you can see here. So these small square elements are basically the reflecting elements. These are the reflecting elements here, and which are basically printed on a dielectric substrate basically. So this is the first layer. Then there is a middle layer. The middle layer is simply a copper plate. If you see, if you can know the behavior of the copper plate, this is basically to avoid the signal or the energy leakage. So the middle layer has a property or been designed with the copper plate so that the no signal or the energy should be leakage. And the last layer is basically nothing but a circuit board that is used to tune that is used to control the reflecting coefficients of the RIS elements. So these are the elements, and this is the controller here. And this controller basically is printed on a circuit board so that you can control or you can manage the surface impedance, and according to the surface impedance you can manage the phase shift of the beam or the signal which is being reflected with these elements in a particular direction. So so basically the third layer consists simply consists a circuit board which is used to tune the reflection coefficients of the elements, which are basically operated by a smart controller. Now what is inside the controller? It is all about the is all about the designers which are actually designing the surfaces. So some people are saying the controllable reflecting elements can be achieved through the mechanical switches, some special material like graphene, some electronic devices like pin diode or varictor diode. Some people are interested to have the controller unit with the help of the Arduino devices, which generally our UG students are using. Arduino devices, Raspberry Pi also can be used to control these surfaces. And one is important as one of the important unit is basically known as the field programmable gate arrays, that is a FPGA kits. Okay, so with the help of the FPGA kits you can also control your surfaces basically. So there is a variety of controller which can control the surfaces, but the basic idea is very simple here. We need to adjust the surface impedance of the elements, and according to that we need to adjust the phase shift so that we can get the desired direction of the signal where the receiver is being placed basically. There are some other names which are being introduced for the RIS, that is intelligent reflecting surfaces. So because the surface is a reflecting in a nature, so the people have said an intelligent, that this is a real-time programmable and controllable surface. So they have also named it as a intelligent reflecting surface. The another name is a software controlled. Okay, because we are controlling this particular meta surface with the help of some Arduino device or maybe some FPGA kits or maybe Raspberry Pi of devices. So because we are providing some sort of software to control our surfaces in a real time, so they have been named it as a software controlled meta surfaces also. So, and there are a few more names are in a literature like large reflecting arrays, large reconfigurable intelligent surfaces. So there is a few more names are introduced in the literature basically, but here the idea is basically more or less same. We just want to control our reflecting beam in a particular direction or in a desired direction where our receiver is being placed basically. So this is the major aim of the reconfigurable intelligent surfaces, and which can, again I'm repeating, this is just simply, so our aim is, because we specifically as a wireless communication, if we look into the wireless communication, we are not interested in designing the surfaces here. Let us assume we have some metamaterial surfaces available with us, with having a ideal conditions and the better properties, and we just want to control this surface with the help of some controller unit by adjusting its surface impedance so that the phase shift can be controlled according to our desired direction or our desired requirement. This is our basic aim. But definitely this is very, if you look into this integration in the wireless communication, it is again a highly challenging problem, okay, which people are generally talking about, because we are controlling the phase shift. So what is happening? So when I'm saying the controlling and programmable radio propagation, so my meaning is if I can control the phase of the beam of the reflecting element or the reflecting signal, so that I can say that I am having the controllable radio propagation environment, because I am able to adjust, I'm able to control the reflecting signal in a desired direction. So this is the basic aim here, and this basically achieved with the help of the artificial metamaterials or the meta surfaces. So there are a few major features of the RIS. So one of the feature is because these RIS are passive in a nature, so they do not require any dedicated energy source for RS signal processing. So basically what they'll do, they are just receiving the signal and reflecting back. That's it. So there is no signal processing unit available for the meta surfaces. So that's why they are very cheaper. Okay, so if you can if you see the your third generation your LT scenarios, the long-term evolution scenarios, which are already been deployed and the people are using, so they generally works on the concept of relaying. If you are been somewhere studied this particular part, relaying, that is a cooperative relaying communication. So instead of, let us say here, so instead of this element, instead of this RIS element, if I'll place a relay, that is some people also know this as a repeater. So let us place some relay element. So what will happen? The signal will transmit to the relay, and then relay further transmit to the receiver side. So this relay entity basically consists of some processing unit, because it will amplify or decode the signal, and then accordingly it will retransmit the processed version of the signal to the receiver. But in case of RIS, they do not have any RF signal processing unit. They are just receiving the signal, and you are just shifting you're just controlling the phase of the signal, and you are transmitting the data towards the signal towards the dedicated receiver. The another important feature is they do not amplify or introduce noise, because when reflecting the signals, and they are just providing the inherently full duplex transmission. Because if you see the relaying technology, what is happening? Your signal is first transmitting from transmitter to the relay node, and from relay to the destination node. Okay, so here what is happening? You are having the half duplex transmission in case your relay is a half duplex in a nature. So half duplex means it is just receiving at a time and then transmitting in the another time, basically. So, but here, because there is no processing unit, no amplification is happening, no detection is happening. So the RIS is just simply receiving and reflecting the signals in a desired direction according to your need. Okay, they can be easily deployed or can be installed on the buildings or the ceilings of the factories, indoor spaces, and they can be hanged on some let's say signboards which are placed outdoors. So you can just simply place these sheets. These are nothing but a metal sheets. So you can place these sheets on the different locations. Okay, and definitely they can be reconfigurable in order to adapt themselves with the according to the changes of the wireless environment. So because they are reconfigurable and can be programmed by the help of the software means. So these are some of the major features of the RIS. So let me introduce the mathematical background for RIS. So before introducing the mathematical background of RIS specifically, let me first give you the some basic detail of the relay-enabled wireless communication systems. So what is happening here? So this is the typical system, which this particular system being deployed in the LTE as well as the WiMAX scenarios also under 3GPP. So what is happening here? The source is transmitting some signal to the relay, and the relay is then transmitting the data to the destination. So now here, everything is basically depends on the relay processing. If relay is disabled by some means, so you cannot transmit us data from source to the destination here. And the relay needs to be allocated some of the resources also. Okay, let's say if the network is if the overall network have a power of, let's say, 20 dB, so you have to give some of the power or some of the resources to the relay as well. Okay, and now there are the various examples. Relay can be a mobile device, relay can be a base station, relay can be a vehicular device, and so on. But here I'm just interested in typically giving you the idea of how the relay enabled wireless system generally works. Okay, so if we are assuming that the relay is an AF relay, that is amplify and forward relay, so what it will do, it will just amplify the signal and transmit it to the destination. Okay, so here is some equations I have mentioned here. So this first equation is basically YR, that is the signal received at the relay node. then this relay node, this received signal YR is amplified by this factor G, which I mentioned here, and you will get a new signal which will be transmitted by the by the relay node. So the XR is the new signal, and this signal will be transmitted by the relay toward the destination node, and then you will get a new equation, that is YD, that is XR. HRD is the definitely a channel gain between relay and destination, and you will get this equation. If it is a decode and forward relay, you just simply get these type of equations. What? Because decode and forward means the relay will decode the signal, whatever is coming from the source. It will decode the signal, then re-encode the signal, and then transmit. Okay, so there is a no point of amplification in case of the decode and forward. So that's why these two equations, or basically the decode and forward relaying, makes these two channels are independent. Basically this HSR, now when you are transmitting the data from relay to destination, there is a no use of this HSR, because whatever signal you have been received through this channel, it has been decoded and then re-encoded and then retransmitted toward the destination. So you will get these type of equations, or the signal received at the respective nodes, receiving nodes, relay and destination. So this typically has the, if I'll talk about the spectral efficiency of this system, this is basically 1/2 log 1 plus some PS by N naught, that is transmit power divided by noise power, that is an average transmit SNR, and the minimum of the channel gains of the 2 hope, that is HSR, that is source to relay, and the relay to destination. So this is the typical spectral efficiency which basically achieved in the relay based wireless systems. Okay, and there is a one more factor available here, is a half. So this is a pre-log factor which is basically introduced because of the 2 transmission phase. So when I'm saying the 2 transmission phase, so my meaning is the one transmission, the from source to relay, and the another transmission is basically from relay to destination. So the overall information exchange from source to destination generally require 2 phases, that is a source to relay and relay to destination. That's why this factor comes into the picture, 1/2. Okay, now this if we see this this background for the relay and RIS enabled wireless system. So let us consider this example. There is a transmitter which is transmitting some signal towards the RIS, which is having the N elements. That is N, the RIS sheet is basically consists of N reflecting elements, and then this basically then further radiated or reflected this signal in a desired direction of the receiver. So let us assume the channel gain between transmitter and RIS is HI, and redirected or RIS to the receiver is a GI. This I is basically, I have mentioned here, the I is basically denoting from 1 to capital N, all the elements, because if it is H1, that is transmitted to the first element. If it is H2, this is transmitted to the second element, and so on. So the typical signal which will be received at the destination or at the receiver will be look like this thing. The summation of all the signals, I from 1 to N, HI, that is this component, multiply by the GI, that is this second gain, and there is a RI. So RI is nothing but the response which I mentioned here. The RI denotes the ith meta surface response. So because you are adjusting your parameters with the help of the RIS, so what is the response by the meta surfaces, that is basically denoted by the RI. And this RI is basically a function of this phi I theta I of e raised to the power of j theta I, where this phi I basically denotes the reflection coefficient produced by the ith reflector element of the RIS, and this theta is your phase shift, that is a theta I, which is or a incidented angle basically, or the ith element basically. So sorry, this is the reflecting angle which you need to adjust, basically. So this is theta I, and I have mentioned I here because of the all elements, because you can assume like this, because I is basically denoting for 1, 2, and capital N. So this is theta 1, theta 2, and theta n, which means theta n for first element, theta 2 for second element, theta n for the nth RIS element. So according to that, you can have the different phase shifts basically, where this particular is known as the reflection coefficients, which is basically generated by the ith reflecting element of the RIS. But the interesting fact here is, if you see the spectral efficiency of this system, it is simply the log base to 1 plus PS by N naught. If you can see here, this is okay, this is fine. Now it is changed here. If you see this particular part, if you see here, it is a minimum of 2 components. But as I have discussed earlier, that it gives you the inherent full duplex transmission. So because there is no point of having the half duplex here, so that the signal is basically first coming from transmitter to the receiver, reflecting element, and then it will process some data, and then it will retransmit it to the receiver side. So there is no point of here in the RIS enabled wireless systems, where if you see this particular relay based system, here is a point of half duplex nature. So that's why you got this 1 by 2 also. So, and the minimum of these two. So here it is just simply the n square, that is the number of element of a square, and HSR and HRD, that is simply. So I have mentioned HSR basically, or you can simply use the HI also or GI also. But I just want to compare these two with the help of the relay based. So I have mentioned here HSR and HRD. However, the meaning is same, HI or GI of square you can mention here. Okay. So this is the typical spectral efficiency difference, and you can observe if you have the two gains, let's say the gain of this and the gain of this, so it will choose the minimum of these two, whereas it is multiplied of these two gains. It has been multiplied 2 gains, and further it has been multiplied with the n square. As the number of elements are increased, the spectral efficiency is further increased. And as we have seen in the first slide, the spectral efficiency is of a basic requirement of the future communication systems, future wireless communication system. So even with this, we can observe that we can get the higher spectral efficiency if we see this particular phenomenon. But there are some advantages also. Let me introduce here. What is happening here? Here's the, if you see the relay enabled systems, it is amplification at relay, and it is a positive sign, because if the signal is being distorted, so relay will amplify the signal and forward it towards the destination node. But there is a pre-log penalty in the spectral efficiency, if you can observe. So there is a pre-log penalty here. But at the same time, the positive sign is no pre-log penalty here. That is fine. But this multiplication of channel gain basically. So this is the drawback. And this drawback is basically from the point of view of mathematical difficulty basically. If you see here, if I'm interested in this particular example of relay based, the minimum of these two, this is much simpler. For example, let us assume a case. If HS square is exponentially distributed, as we have seen yesterday also, so here what I'll calculate the minimum of the sum exponential distributed comma the exponential distribution. But what is happening here when I'm saying this is exponential distribution, this is also exponential distribution. So now I am having the product of 2 exponentially distribution random variables. Okay, so then definitely there is a mathematical challenge while we are simplifying our performance basically. However, the spectral efficiency, because of the introduction of this n square, is more compared to the relay enabled wireless systems. And the people have also proved this by the help of some experiments also. But these experiments are only only introduced for the, or only validated under the indoor environment rather the outdoor environment. So the people are more interested in the indoor environment first, because definitely when you will go to the outdoor environment, there are the more other things which needs to be incorporated in the system design basically. So if you compare these two RIS and relay systems basically, So I have just mentioned some of the parameter here, that is the RF chain, some signal processing capabilities, some noise, duplex nature, hardware cost, and the power consumption as well. So the if you see, the RIS does not require any RF chain because there's no RF processing unit here. No signal processing unit is required. No noise amplification kind of thing is available here. Duplex is a full duplex nature. Hardware cost is very low because metamaterials are very cheap, and the power consumption is very low because there is no RF processing available. So it is just a reflection unit. So whatever the signal is coming to this surface, it is just being reflected toward the particular direction. The only power consumption is basically to control the phase shift and the reflection coefficients of the sheet according to the adjustment of the surface impedance. Whereas if you see the AF relay, that is amplify and forward relay, decode and forward relay, and full duplex relay, so they have their own units. They require the RF chains also. They require they are basically half duplex in nature. They are introduced with some noise components. The hardware cost is definitely involved because it's a physical entity, and which is basically built with the help of some antennas and other devices also. Okay, so and if you see the full duplex nature, definitely it's very high. And one more drawback, if you can go through the literature, one more drawback you will found for the full duplex nature of the relay, that is a self-interference basically. So such type of relay are basically introduced with the self-interference also. So there's a huge complications and the challenges are available or in the relays. Whereas in comparison to the relay, the RIS is more simpler and more or basically less complex. Okay, it has also been seen that the RIS has the potential of replacing these relays in many applications, which are basically operating at the higher frequency band, like millimeter waves in 30 to 100 gigahertz, or in the sub-millimeter range, like some greater than the 100 gigahertz of frequencies. So you may use these RIS at the higher higher frequency ranges, because the people are currently looking for the millimeter waves and the sub-millimeter waves scenarios. So basically if we are talking about the sub-millimeter wave, so we are actually dealing with the terahertz frequency ranges. So we can also enable the terahertz wireless communication scenarios with the help of the RIS. But there are some major challenges in RIS also. The few challenges I have mentioned here. One is, let's say, a channel state information acquisition. So it is again a very important challenge. That is, we need to estimate the channel, and it is very difficult to estimate the channel between the transmitter and the RIS, and the transmitter and the RIS to the destination, because your RIS do not have your RIS's device basically, or sheet, you can see the elements do not have any RF units basically. So they are just simply the passive devices. Okay, so if they are passive devices, then it is very difficult to estimate the channel between this source and the RIS, and also between RIS and the destination. So this is one of the prime concern or one of the challenge basically, how to calculate or how to get the accurate information about the channel state information, or how to estimate the channel state information basically. The another important aspect is the low complexity robust system design. Definitely, if we are looking for a new technology and we want a flexible design, so this design at the same time should be a low complex, should have the low complexity. The security and privacy control. This is a very important field and a very important challenge as well, or a major challenge for any wireless communication system. Because if we are assume it like this. With the help of the RIS, for example, if you are able to control our phase of the element, which means that okay, so what we are actually let me discuss in that way. Basically, if you see in the yesterday class, what we were discussing about the physical air security, there is a transmitter and there is a receiver and there is a eavesdropper. So the transmitter is transmitting some information or broadcasting some information, and the receiver which is a legitimated receiver. Definitely we want to transmit the information towards the legitimated receiver only, but unfortunately at the same time the eavesdropper is also trying to fetch the or also trying to intercept the information which was transmitted by the transmitter. Now what is happening in this particular RIS case, if we are saying the RIS, with the help of the RIS device, we are able to control our phase, or you can see the beam, basically the reflecting beam. So if you are able to control the beam, which means it may happen the eavesdropper which is sitting, or which is which is available in the network, may receive the this may receive the controllable beam in that particular direction. Okay, and this, how this can be happen, this can be only happen if the RIS is also acting as a some wiretap or maybe some untrusted device, basically, because it may happen the RIS may be untrusted device. Okay, because for example, we have placed, or we have we have installed a array of elements on some wall, but at the same time some another wall, so some another array of the elements was also placed near to that wall. So once our signal has been reflected, okay, so it may happen it will also be reflected with the nearby reflecting array, which is definitely was not installed by us for which is not basically installed by us, because it is an untrusted part, basically it is an untrusted part. So let us consider the RIS is also be untrusted elements. If they are untrusted elements, so they may control your signal in a direction which is not favorable for the legitimate receiver, but it is favorable for the eavesdropper element. So there are the various concerns also while we are controlling there, because if you are able to control, and it's a software programmable, so if someone is hacked our program according our software part, so it can be controlled accordingly. So there are the several security and privacy issues also introduced as we introduce the RIS. Okay, but here the another the important, which basically we are interested in the channel modeling. Because as I mentioned in this previous slide, if you can see here in this spectral efficiency slide, when I'm saying there is a multiplication of channel gains, so the multiplication of channel gains has introduced another challenge. Basically, the multiplication of these two gains have introduced another challenge of this model, basically of the channel modeling between the transmitter and the RIS, or the RIS and the destination or the receiver, basically, because now they have been imposed a various other aspects of the statistics of the probability and statistics theory, basically. So again, we need to understand how the channel can be modeled between these two, and because if we are able to model our channel perfectly, then only we can analyze our system performance, and that system performance then can be used to can be used by the designer while they are deploying and develop the different RIS enabled wireless communication system. So this is the basic of the RIS, although there is a huge to study and huge to read about the RIS and the wireless communication, and the RIS enabled wireless communication. But specifically here, I am interested in the channel modeling of the RIS. So let me first introduce about the one simple scenario which I am considering for this channel model. So let us consider a simple example or a use case, basically a case study. So there is a transmitter. There is a transmitter which is transmitting some information to the receiver, but unfortunately, due to the heavy path loss and shadowing, the direct link between the transmitter and the receiver is not available. So, but we are fortunate that we have another extra path which is through this RIS elements. Okay, and this there is assumed there is a n number of elements are available in the RIS. So the transmitter can transmit its information from so transmitter to the RIS, and then RIS will reflect the signals by adjusting the phase shift or the reflection coefficients of the input signal toward the desired direction, that is the receiver side. So that you can assume as a simple basic example. Okay, So this we need to analyze. The behavior of this system needs to be analyzed. Okay. Now let us consider a few simple assumptions here. The HI and GI from transmitter, the channel between transmitter and the RIS, and the RIS and the receiver are assumed to be independent because they are totally and the slowly varying flat feeding scenarios. They are simply independent to each other. Okay, and they follow the Rayleigh distributions. The individual HI and GI follows the Rayleigh distributions with the scale parameters being equal to 1. That is their variances are equal to 1. So I have assumed the HI having the variance is omega HI and GI gain having the variance is omega GI, and it is equal to 1. Although we should not consider is equal to 1 because it's an ideal condition. Although okay, typically we generally assume the omega HI is basically modeled as the distance between the transmitter and the RIS element, and the omega GI, that is a variance between RIS and the receiver, can also be modeled as with the help of the distance between the RIS and the receiver end. But we can consider this to be 1 under the situation that, or under the fact that even the line of sight links are basically you can say are blocked. Basically, if the line of sight are blocked between source to the or the transmitter to the RIS and RIS to the receiver, there is still some scatters available. So if there is a, even after having the line of sight is blocked between the transmitter and the RIS, there are the certain scatters, the extensive scatters are available, and with the there is some mathematical observations behind this. By considering this situation, the line of sight between the transmitter and this is unavailable or blocked, but there are some extensive scatters are also available between transmitter and the receiver, between the transmitter and the RIS elements, or between RIS and the receiver. You may consider these variances to be 1. So for the sake of simplicity also, let us assume these to be 1. However, there is a practical justification also, which I have mentioned here, that is even after they are blocked, but there are still some extensive scatter which are enables to make it to be 1. Okay, so this is the basics of or the basic assumptions we are assuming here. Now let me introduce the different equations related to this, or the modeling of this particular system model basically. So if you see here, if it is HI, and we know that I is basically varying from 1, 2, and all the number of elements which are available, 1 to capital N. So I can write my received signal, that is YD. This is at receiver basically. This is at receiver. So it can be written as H1 G1 R1X plus H2 G2 R2X plus Hn Gn Rn X plus some noise at the receiver side. So these elements basically H1. The H1 is the component between transmitter and the first element. The G1 is the channel gain between the first element and the receiver. The H2 is the element. H2 is the channel gain between the transmitter and the second element, and so on. And similarly, the R1 is basically the reflection by the first element. This is R1. Similarly, the reflection by the second is R2. Accordingly, these are the reflection elements like this. So if you combine these together, so we can write like this: HI, GI, RI, and this is X plus ND. And similarly, again, we are assuming we are transmitting a signal X with the help of some power, or with the power of ES. So this is our assumption or consideration at the transmitter side, that we want to transmit a symbol X with the power of ES. Okay, and at the same time, as I have already mentioned previously, that this ND is nothing but the additive white Gaussian noise with zero mean and some, let's say, N0 variance. Okay. Also, I have also mentioned this Ri, that is nothing but the phi I of theta I e raised to the power of j theta I. Where I've mentioned this particular part is known as the reflection coefficients, which is produced by the ith reflector element of the RIS, and this theta I is basically the phase. Okay, so for a typical assuming or although there are the various, here I'm not going to analyze the phase reflection coefficient basically, which is produced by the reflector elements. So for a meantime, we are assuming let us assume because our main aim is to model the channel behavior, okay, rather than focusing on the reflection coefficient part. If you want, you can also optimize the reflection coefficients according to the mathematical background which has been derived from this model. Okay, so or by having the some objective functions. So assuming your phi, that is a reflection coefficient, is basically equal to 1 but this condition is basically under the ideal phase shift scenario. So ideal phase shift scenario, I'm assuming that my signal which is being incidented, it is ideally being shifted or being phase shifted toward the desired direction of the receiver. So I'm assuming this is to be 1. So under this particular condition, we can assume to be 1. So this Ri is now only e raised to the power of j theta I. So now this can be only available in terms of e raised to the power of j theta I. That's it. So this is my new reflection or the response of the meta surface, basically Ri. Okay, so finally I can write like this. My Yd, that is a received signal, can be written as I is equal to 1 to n hi gi ri of x plus some nt. Okay, let us assume this is equation number 1. At the same time, because we know that and this is another assumption, although just now I have told you that it is a challenge, that is a channel state information acquisition is one of the major challenge in the RIS enabled wireless communication. But for a meantime, let us assume that RIS has the full knowledge of channels phases of HI and GI, because it has been, you can assume it is a full knowledge of the estimated part basically of HI and GI. So according to that, we can express, let us assume my HI can be expressed as HI of mod e raised to the power of for example phi of HI, and GI can be expressed as G of I e raised to the power of minus of phi GI. So this we can express here. Okay, so this is nothing but the HI is basically the magnitude of HI and e raised to the power of minus j phi HI, where HI and GIs are basically the Rayleigh distributed. And I have already told you that the Rayleigh distributed and their scaling parameter, that is omega HI and omega GI, are basically equal to 1. So I'm assuming they are having zero mean and variances is equal to 1. So if you can express this signal, and we know that the response of the meta surface is also equivalent to this, by assuming the reflection coefficients under the ideal phase shift is equal to 1. So we can express our equation like this: mod of HI e raised to the power of minus j phi HI mod of GI e raised to the power of minus j phi GI, and then e raised to the power of j theta I, and this x plus of nd. Now this is our signal, this is our received signal, which is of our interest to analyze the performance of the system. But again, if you want, again there is an assumption. Although you can control, you can have the some sort of, or you can plan some sort of algorithm to get the maximum benefit of the RIS, and the maximum benefit of the RIS can be only achieved when theta I is equal to phi hi plus phi of gi. If it is equal to this, you can get the maximum benefit of the RIS. Or in terms of the communication measures, you can get the maximum SNR, the instantaneous SNR, only when the theta is equal to the phi hi plus of phi gi. Or you can get the maximum benefit from the RIS under this condition. So here this is the assumption basically. Although we need to prove it with the several optimization problems, whether we are able to achieve this relation or not. This theta is equal to phi of hi plus phi of gi. But for a assumption, in order to assume that our RIS is designed in such a way so that we can get the maximum benefit from this, so we can assume this relation to be true. So once it is true, so my YD is basically simply written as I is equal to 1 to n h of I mod g of I plus noise nd. That's it. So this is my received equation at the receiver side. Mod of this, and here is the signal also x. So let me write here. So this received signal is basically yd is equal to summation I is equal to 1 to n hi of mod gi of mod of x plus nb. So this is our received equation at the receiver side. Or let me introduce in this way. Yd is equal to a times of x plus nd, where I'm assuming the a is basically this quantity, and here from this representation, that is a is equal to summation of hi and gi, I have to introduce the channel modeling basically, because my channel is not yet modeled properly. I'm not able to get what is the actual behavior of my channel, my channel between transmitter and the receiver. So if you see the basic scenario of this equation, you will observe the hi and the gi are individually the Rayleigh distributed with some zero mean and the 1 as the variance. But we actually need to know what is the distribution of this overall quantity. And now from here, the discovery of channel modeling is generally starts. How to model this particular behavior. So before going into this, let me also give you the as we have also seen in the yesterday class, that is the SNR, the instantaneous SNR. So instantaneous SNR can be simply written as, let's say, delta d, lambda d. The power is PS divided by some n naught, and signal term is basically A, so we can simply write like this. So this is our SNR. This is the instantaneous SNR. But the performance matrices like bit error rate, outage probability, ergodic capacity, which are related to the instantaneous SNR, can only be calculated if we are able to calculate the behavior of this A, because this is mandatory to obtain initially. Okay, so let me give you the quick review how to calculate this A basically, and from here only you will get the different flavor of our statistics basically. So the A is basically here I is equal to 1 to n hi and gi. Now if you see here, this is Rayleigh distributed, and this is also a Rayleigh distributed. So if you see these two, they are only, if you see these two are product of two Rayleigh component. So can we write, or can we assume these are the double Rayleigh distributed? We can assume these are the double Rayleigh distributed. So and if you see the PDF and CDF of the double Rayleigh distributed, so you can write like this. So let me introduce the double Rayleigh I'm assuming this quantity to be AI, for example, AI. So AI is equal to only mod of this, so that I can introduce the AI component here. So if you see the PDF, it will be x of k naught of x. It is I'm not writing here the magnetic, the variances as I have done in the previous lecture, because I have assumed the variances are 1. So I'm just writing the CDF of PDF with having the variances to be equal, variance is equal to 1. So this is some x times of k1 of x, like this. So these are the PDF and CDFs of this. But what is happening? Even after, if I'm assuming that this quantity HI and GI is double relic distributed, so here what is happening? My A is actually the summation of double relic distribution. Double relic distribution, which means we need to have the sum of double relic distributed elements basically, and the getting the CDF and PDF is very difficult. Is very tedious job. Even you will not found the CDF and PDF in a closed form basically, in a form which is appropriate for the designers basically. You won't get the appropriate designing, the cumulative distribution function and the probability density function, the sum of double Rayleigh elements basically. So from here we need to rethink that what will be the appropriate model then, how to get the appropriate model for this capital A basically. So if you see this quantity, which is A is equal to I is equal to 1 to n. So the people are, although there are the several models they have designed, so the people have basically designed 2 approximations. One is known as the CLT approximation, another is known as the gamma approximation. So as per the CLT approximation, what the CLT suggests? So CLT is basically the center limit theorem. So as per the center limit theorem, if you see the center limit phenomena, so it states that under certain conditions, the sum of many random variables will have an approximately normal distribution. This is basically the center limit theorem. And if you see that, if this is the double Rayleigh distribution, the multiplication of these two is the double Rayleigh distribution. So sum of these two may be approximately expressed as the normal distribution, that is the Gaussian distribution. Okay, so this can be written as the Gaussian distribution. So this is one of the approximation, which is known as the center limit theorem approximation. The another approximation, which is given by the gamma approximation. So they have suggested that this double Rayleigh, the summation of this double Rayleigh under certain conditions, like or let me introduce like this. Whenever you are having some sort of situations which are not mathematically tractable in a closed form, so we need to use some numerical methods, numerical approaches basically, okay, which are like Gauss logarithm methods, Gauss quadrature methods. Okay, there is a variety of polynomial or expansion methods are available in the literature. So with the help of these methods, we came to know that this particular approximation, this particular basically model can be first represented with the help of the Gauss logarithm method. So there is a one very popular approximation method in the mathematics, that is a Gauss logarithm quadrature method, and this suggested that if you further approximate this Gauss logarithm method, you will get the gamma approximation. So there are the 2 approximations which are basically available for this this type of situation where you are having this sum of random variables, and the random variable is basically double random variable. So you may have the gamma approximation as well as the center limit approximation, center limit theorem approximation. And in the literature, it is been proved that the gamma approximation is performing much better compared to the center limit theorem. Under certain conditions, they've been proved and they have been validated by several results that the gamma approximation is much better compared to the center limit theorem. Okay, so let me quickly give you what is the gamma approximation, PDF and CDF of this particular equation here. So if you see this A and this we want to calculate, because even I have tried also to calculate the PDF of CDF of A directly by assuming that this is nothing but a double Rayleigh fading and there is a sum of double Rayleigh fading. So although we have an approach which is known as the characteristic function or the moment generating function, with the help of this we can try to obtain, but it is very difficult to get in the closed form. So we definitely go to the sum approximation. Either you have to use the this center limit theorem approximation or maybe the gamma approximation. There is one more approximation which is known as KG approximation, KG distribution. This is also another distribution which can be approximated, which can be used to approximate this particular type of scenario. Okay, but I'm much interested in the gamma approximation because it is widely and popularly used and can be easily can easily be help us to evaluate the performance of the systems. So if you go into the detail of this approximation of gamma with the help of the Gauss-Lagrange method and some approximations under certain conditions, so you will found the PDF of A, will be expressed like in terms of the gamma distribution. B of A plus 1 exponential of this, and the CDF can be written as 1 by of A plus 1 gamma. This is the gamma which I was talking about. That is a upper incomplete gamma function. Incomplete gamma function. And here it is 1 plus A comma x by of B. So this is the gamma approximation. So because it is also very easy to relate with the even you have been observed this particular phenomenon of gamma approximation in your Nakagami fading channel when you are evaluating the performance under the Nakagami fading channel. It is commonly used function basically. So this can also be treated like this. Okay. Now, so this A and B are also the parameters. So they have defined these A and B separately. So the A is basically related to like K1 square by K2 minus 1, and the B is basically related to the K2 divided by K1. Okay. Or and this K1 is basically the mean of A, and K2 is basically the variance of A. So even you can calculate these means and variance basically. So if you want to calculate the mean and variance, just give me a so you will get the values like n pi by 2, and here you will get the 4n 1 by pi square by 60. These values you will get with the help of the by calculating the mean and variances of the this capital A. Okay, and here I'm just if someone is interested to calculate, you can calculate these very easily. So I'm also writing the PDF and the CDF of HIs because under having the amplitude 1. So if you want to use, you can use these PDF sensitivities. This is x of p minus of x square by 2. And if you want to use the PDF of this, it is 1 minus of x square by of 2. So you can use these PDFs and CDFs to obtain the this thing. So here you will get gamma function. So this is basically the gamma approximation, and this gamma, sorry, I have mentioned here is it is basically lower incomplete gamma function. Lower incomplete. If you want to write this lower incomplete equation, you can write like this: sum 0 to x t minus 1, or let it be alpha, and e raised to the power of minus t into dt. So it can be represented like this. So it's a lower incomplete gamma function. Okay. So this basically can be represented in terms of the gamma approximation. If you go into the detail of the center limit theorem, it is also available. So as per the center limit theorem, you will get the some normal distribution, that is the Gaussian distribution. Okay, and then accordingly you can calculate the probability. The performance of the system. Okay, but why this this is more interested, the gamma approximation? Let me give you a quick review why this is more interested. So let me so we know the knowledge of the A now. The A is nothing but the gamma distributed, and we have the PDF and CDFs are available. PDF and CDFs are available with us, so we can calculate some performance measures basically. Let me calculate the performance of this system. Performance in terms of the, again, I'm using the same metrics which I have used yesterday, that is probability, outage probability. Okay, so if you see the outage probability definition, so the P out is nothing but the probability of C, that is a channel capacity, is less than the target rate. So here C is nothing but the log base 2 1 plus of SNR, that is instantaneous SNR. So I can write here the probability of log base 2 1 plus gamma D is less than R, and if you manipulate it, you will get the probability of gamma D is less than 2 raised to the power of R minus 1. This is the outage probability. Now further, if you see, we know that the gamma D is nothing but the PS by N naught of A square. So you can invoke this into this particular equation, and your P out will be simply the probability of PS by N naught A square less than 2 raised to the power R minus 1. And if you simplify, finally you will observe this is nothing but the probability of A less than N naught by PS 2 raised to the power minus R of this and the root of this, which is nothing but a very standard theory of probability. That is, this is the CDF of A having the argument equal to this 2 raised to the power of R minus 1. So this is the outage probability. So now if you see this particular formula, and we already calculated the CDF of A in the previous slide, that is this 1 by of A in the lower incomplete gamma function of 1 plus A of X of B, X by of B. So your outage probability is very simple. If you can see here, the outage probability is very simple, and it will be 1 by of A plus 1, that is gamma A plus 1. This sign is basically for complete gamma function. This is for the complete gamma function. And it is simply be expressed as A plus 1, 1 by B, and this is N naught by PS 2 raised to the power of R minus 1. That's it. So this is the outage probability of this RIS enabled system, which is very easy to evaluate and which is easy to understand from this. And this is as per the gamma approximation. Gamma approximation. Let me complete gamma approximation. On the other hand, if you see that if it is assumed, if my A is assumed to be expressed as with the help of the central limit theorem, with the help of the CLT basically, then it is slightly difficult, because if you go into the detail of this central limit theorem in the statistics, basically, if A is a Gaussian distributed or Gaussian random variable, basically, for basically this, let me clear here, this case, if it is approximated with Gaussian distributed with some mean, let's say mu, and some variance omega, because definitely if we are calculating the if we are applying the center limit theorem with the some and it is been approximated with in terms of the Gaussian distribution, so it has some mean and variances. So my at that time my a square, because why a square? Because in SNR, if you see here in an instantaneous SNR, it is a square. So a square is basically expressed in terms of the central chi-square distribution, or a non-central chi-square distribution. And you know that the chi-square distribution and the non-central chi-square distributions are very specifically the non-central chi-square distribution. Dealing with the non-central chi-square distribution, it's required lots of effort compared to the if you are comparing it to the gamma approximation. So the even if you see the the PDF related to the this gamma approximation, basically sorry, this central limit approximation. So let me express here. So the approximation for this a square, it's very difficult to further manipulate. Let us this y, sorry, let me give you this y minus 4 I minus of half m root of y divided by of omega square, and e minus of y plus some m square divided by 2 of sigma square, where sigma square is nothing but the noise component. So this will be the our PDF, and accordingly we can calculate the CDF also. But this is the PDF under the CLT approximation, and this I is the Bessel function here, or m is the mean component, basically mean component, which I have mentioned in the previous with the help of the key one. Okay, so this is the mean component, and this is the this center limit theorem approximation. So this particular approximation is a little difficult to deal. Rather the gamma approximation, which is widely available and widely used in the literature, and the several formulas related to the this gamma approximations are also available for so that it can be easily designed and deployed accordingly. So this is how we can calculate the performance. This is first so the idea is we need to properly model the channels statistics of the channel statistics of the links between the relay and the between the transmitter and the RIS, and the RIS and the receiver, and according to that, then we need to express our performance analysis, or we need to analyze the performance of the systems. So if you see this, let me share the Mathematica version of this, how to code it. Again, as we have used in a previous lecture, basically. So again, I have used the same Mathematica tool to evaluate the values from this values, or to validate this particular expression, basically. So here it is very simple to write. First, I have initialized all the parameter which I have used, like rho HO, that is PS by N naught, that is a transmit SNR. R is the target rate. NS is the number of component, basically, which are used. That is the number of reflecting elements, NS. So I have used NS in the Mathematica specifically because if I'll use the N here, so it will not evaluate, because N is a some already used parameter in the Mathematica. So that's why I have mentioned as the NS. You can use any parameter to evaluate. It's just the understanding purpose. K1 is the parameter, which is NS multiplied by 2, which I have already mentioned, and according to that, I have mentioned each and every parameter. Then I have initialized the out, that is P outage, basically the outage probability, and this is the very simple code, a 2-line code, because the expression is very simple here. Okay, so this can be evaluated, and then you can get the values for different different SNR in dB, that is from 0 to 40 dB at difference of 5 dB each. Okay, so you can get these values, and then you can you can copy these values to this MATLAB simulation, basically. So let me share the MATLAB simulation. Yeah, So I think it's visible. This page is visible.
Sir.
Yeah. So here again we have used the same approach as we have done yesterday. I have used some 10 raised to the power of 5 independent iterations, and then I have initialized my target rate, then threshold accordingly, and initialize the counter basically. Then I have set the SNR dB in 0 to 5 to 40 dB. Then I set the power, that is 10 raised to the power of, because I have first need to convert it in the linear scale so that each value can be easily evaluated. And now here, if you can see in the yesterday problem, we have used the XP rend, but here we have used the relay rend RND function basically. So because if you see this this expression here, so what I have mentioned here initially, the this this HI mod and GI mod basically both are relic component, relic distributed. So I need to calculate the relic components. I need to generate the relic numbers basically. So when I'm generating the relic numbers, so I'm using this RAYL and RND as a command. And because this is 1, because I have assumed the variance to be 1, so I'm using the relic rend 1. Okay, in the argument basically. Similarly, GI, so I have used this as the parameter. And then we know that my SNR, if you see the SNR here, my is PS by N not A square. So A is what? This is HIGI of square. Because here, remember in this particular case, I'm using only one component, H1G1. If someone is interested, you can also write like this. You can write like this. This is H2, the second component. G2 is the second component. Accordingly, you can have the H1 G1 plus H2 multiply G2 and then square. So you can make a sum of, you can just need to generate the number of variables according to the use of or according to the consideration of the elements basically. So initially I have used one element, so I have only generated H1 G1. And if you have two elements, you can generate H2 G2. If you have three elements, you can generate H1 G1, H2 G2, H3 G3. Or if you want to make a system generalized, so you can generate like this: H1 1 comma ns, and this is 1 comma ns. So ns is the number of elements. So whatever number of elements you will provide, that number of channel will be generated, and according to that you can calculate the your end-to-end SNR. So this is all about the just how you treated your simulation part basically. So if you want to generate for 4 components, so just generate these all 4 components separately, or you may generate through a single generalized formula or a generalized representation basically. Then again, it's a very simple, because you have to apply the if and end conditions for the outage probability, that if the end-to-end SNR is less than some threshold, which is 2 raised to the power of R minus 1, which I have mentioned earlier also, that is I have initialized here. And then accordingly, you can run the counter for, or you can average for all independent trials, that is 10 raised to the power of 5, and then you can plot it. So this is the basic, very simple program for this particular system model basically. So if you run this example here, I have used only for one. That is, I have used only a one element, so that's why I have only used H1 and G1 as a components. Again, I'm repeating, if you want to generate for a large number of elements, so you need to generate the number of channels according to the number of elements which are you are basically using. N is equal to 2, 3, 4, 5, and so on. So then you will see the whatever the values we are obtaining from Mathematica, we have copied to the MATLAB in a and then it needs to be verified with the help of the simulation. And now you can observe this figure here. So this the solid line is basically representing the our Mathematica results, that is analytical results basically, or numerical parts, numerical values, and the square values are basically the simulation, Monte Carlo simulation results, or the points. And you can observe they are quite tight till this value, because here I am only considering 10 raised to the power 5 average trials, basically independent trials. And this needs to be further increased like 10 raised to the power of 6, which definitely takes some more time to give the results, although, but you will get the correct and the tight result at the end. So let me share the one example here. This one I have plotted for 4 different values, and this particular program was run for 10 raised to the power 6 independent trials, basically. So you have seen all the analytical results and the simulation results are perfectly matching. Okay, and we can also observe that the n is equal to 1, 2, 3, 4, basically. So as the number of elements, basically, as you can see, as the number of reflecting elements are increasing 1 to 2 to 3 to 4, so the outage probability performance is going to be increased drastically. So you can simply observe here. So for n is equal to 1, at the 30 dB you are only achieving around 10 raised to the power of -2, but when n is 4, when there is a 4 reflecting elements, only at 15 dB you are achieving 10 raised to the power -8 as the outage probability value. So the performance is quite significantly improved when you are applying the n is equal to 4. This although there is I have not presented here the comparison between the relay performance and the RIS performance, but it has been seen that the RIS performance is much better compared to the AF relay scenarios, okay, or the relaying systems, basically. So this is this is how we need to model our RIS. This is the and which I have discussed here, the basics of the RIS and how to use in the wireless communication, how to model the channel, and once we are able to model the channel perfectly, then we can integrate it in order to get the performance of the systems in terms of the outage probability or ergodic capacity, bit error rate, or some other matrices as well, which are interest, basically, which is our of interest. So we can calculate this thing. So, however, this is open field. The RIS is just now started, few years back, hardly of 2-3 years back it has been started, and the lots of works are available, and lots of areas are still open. Specifically, the one of the area which is open, that is a physical air security in RIS, enabled wireless communication, which is slightly a tricky and difficult part because of the channel model, because we need to understand, and we need to deal with the different channel statistics. And you know that the physical air, once we are dealing the security concerns, there is additional channels also appear in the picture. So we also need to tackle with the additional channel. So this basically imposes a huge complications in the performance analysis for the designers, but definitely is a very open field for the investigations. So this is from my side. So the floor is open if you have any questions, so we can answer, so we can discuss it.
Hello.
Yes, sir.
Any question from participants, please? Yes. Any question?
I think there was one question someone has wrote in the.
Question,
is there
please?
any is there any limit on the SNR if we are increasing the elements? Yeah, definitely. There is a limit. We cannot we cannot have a number of arrays. Let's say the typical limit is, let's say, after 20 to 50 elements, the performance is going to be saturated very soon. Or in some of the cases, it has been observed that the good performance compared to the relay system, relay systems, being achieved when you have the, let's say, 200 of elements. So, and even there is a constraint on the SNR also. You cannot go beyond a certain constraint of a certain number of SNR, like 1000 dB of SNR you can use. So it is typically you can use a 40 dB and 50 dB of SNR, but you have to manage your number of elements. How many number of elements are sufficient to achieve the better performance? That is a major concern basically. So as you can observe here, n is equal to 4, only 15 dB of SNR is required to get the 10 raised to the power minus 8 of outage probability value. So there is a constraint, there is always be a trade-off, but it is mainly depends on the number of elements which you want to deploy basically to get the certain performance. So there is always be a trade-off between the SNR also as well as the number of elements you want.
Any other question, please? Any other question? You can, I think you can directly ask the question, then mute yourself after asking the question. You might be wondering, all of you, why we are dealing with such type of mathematics in communication system, because we cannot help it. Communication and mathematics go side by side, because you are dealing with some kind of probability density function, and most of the PDF that we deal in the communication are basically exponential in nature, either exponential minus x or exponential minus x square, or whenever you want to calculate some quantity of interest, whether mean, variance, or whatever, then you can get x into a exponential something, these kind of terms. So unfortunately, these closed form are not available, and closed form solutions are not available. Then
Yes.
you are required to deal with some kind of functions like Q function, gamma functions, things like that.
Yes, sir.
So
Yes.
that is the basis, because we are dealing with such kind of things basically.
Yeah. Even so,
So,
the best thing for this gamma approximation is, if you see here, the
yeah.
PDF, even the gamma approximation can be easily represented in terms of the basic elementary function of exponential.
Yeah,
If you
yes,
expand
yes,
it.
yes.
So,
Yes, yes.
so this can easily be integrated if someone wants to deploy it on the FPGA kits basically, or to test the performance basically. Whereas if you
yes.
see the CLT, it is very difficult because we have to deal with the Bessel function directly.
Right. So that's why we are dealing with different kind of mathematics in communication domain. That is the
Yes,
reason
sir.
actually.
Yeah.
So we cannot help it because we have to use it.
Yeah.
That's all. Nothing else.
Yes, yes. But few things we can observe for the designers so that they can directly use them.
And I appreciate Dr. Sunil that he explained the things very nicely, and he also explained how you can get the analytical results using this Mathematica. And then you can go for some kind of Monte Carlo simulations where you generate some random numbers as per their distributions, and then you calculate the quantity of interest from simulations. Then you can verify your results with the query and the simulations. So basically, so he explained all these things nicely, and he also introduced this concept of reconfigurable intelligent surfaces, RIS, a new paradigm in this wireless communication. And we can see, we saw it rather, how well it's performing. So this is a very good area of research. Anyone who want to pursue this can take up this in this
This is
direction.
very interesting, sir. Just now, if someone is interested, you can visit to my website. One of the paper related to the RIS we have just published in IEEE Access. It is very interesting. You will get some information related to how to model and how to apply the RIS in the physical communication, basically in the wireless communication. So it is very interesting. You can go and you can read it. I request to the candidates if they are interested in the RIS. It is a very it's a very emerging domain for wireless communication. The people are totally focused toward this. Specifically, if someone is interested to design a test bed, you can also design a test bed for the indoor communication. So you just need a RIS device and some SDR kits to do that. So you can also do that.
So if there are no more questions, then I can thank Dr. Sunil for giving such a valuable talk to our participants. And please feel free to contact him or any other speaker also, wherever you want, so that you can interact more also.
Okay.
So, and to the participant, tomorrow there is going to be a morning session at 9:30. And this session would be taken by Mr. Sandeep Pradhan, and this is basically dealing with the stress, developing a conscious lifestyle, because till last 4 days, actually, we were covering a lot of technical things. Now, so a few things which are very important in our lifestyle also, we need to take care of it. So that is dealing with the stress, developing a conscious lifestyle. 9:30, we are going to meet again tomorrow, all the participants. Till then, okay. And thank Dr. Sunil for your
Thank you,
sparing
sir.
your valuable time. Yeah.
Thank you, sir. Thank you. Thank you
Okay.
so much, sir.
Bye.
Hello.
Yeah, one can leave now. Yeah, thank you.
Hello. Hello.
Yes, hello. Speaking, yes, hello.
Good afternoon, sir. Sir, I
Good
ask
afternoon.
one thing. For tomorrow, there is an objective